So in this screencast, we're starting to talk about actual bonding, putting atoms together. And there are three kinds of bonds that we are going to talk about in this course. One of which we're going to talk about for a little bit, one of which we're going to talk about a lot. The other one we're going to talk about very, very briefly. So a bond is really just an electrical force between two atoms. Two atoms come together and there's an electrostatic attraction. There are three main flavors of bonds. There are ionic bonds, which are cases where one element has given up electrons to another element. So we actually have a positive and negatively charged species. The species losing the electron is obviously the positive cation in the system, connected to the anion that it gave up its electrons to. And so you actually have a +1 and a -1, or a +2 and a -2, or a +1 and a -2. Some combinations of ions, actual charged species, that are held together in a three-dimensional matrix. So, for example, sodium chloride. Another kind of bonding is what's known as covalent bonds, where the electrons are not actually exchanged, where they go from one to the other like they do in the case of sodium chloride. But in the case of covalent bonds, the electrons are actually shared by both species in a bond. And then the third kind of bonding, just sort of for completeness, we just mentioned it here briefly, is that of metallic bonding, where we have several atoms of the same flavor bonded together, and the electrons can actually move freely throughout. They're not necessarily tied from one electron to another. And metallic bonding is quite different from that of ionic bonding and covalent bonding. And in this course, we're just going to be talking about these first two levels. So covalent bonding, what we're going to focus on first, is based on what is known as the Octet Rule. The Octet Rule is a relatively simple concept. If we look at the electronic configuration for argon, which is a noble gas, we know it is a neon core, and it ends in 3s2, 3p6. We know that neon is a noble gas, has a helium core, ends in 2s2, 2p6. The Octet Rule comes from this concept that the outermost electrons, the 2s, or the s2 and the p6 are filled. That's a total of 8. Hence the term, the Octet Rule. And so what atoms are going to try to do is try to get a noble gas configuration sort of around them. They get 8 electrons around them, not necessarily as their own in like an ion, but get sort of credit for 8 electrons, for 8 valence electrons. Of course, hydrogen only doesn't want octets. It only wants one more electron, but if it gets one more electron, it's like helium. That's sometimes called the duet rule. Now, something you need to understand is the Octet Rule only is really used for molecular compounds. And if you remember what a molecular compound is, that is a component that contains 2 non-metals. So 2 things to the right of the stair step. So carbon, oxygen, sulfur, fluorine, chlorine, non-metals are the compounds we're talking about here. So let's talk about what really a covalent bond is. So here we have two hydrogen atoms that have come together. And each hydrogen atom has one electron, one valence electron, in its outer shell. And each hydrogen actually wants to have 2 electrons in its outer shell, because then it will just be just like helium. So what happens is the 2 hydrogen atoms sort of come together and physically overlap space such that each hydrogen can see both of those 2 electrons. Each hydrogen only owns 1 electron, but sees both electrons. So as far as it's concerned, each one of those hydrogens has 2 electrons in its outer shell. So each one of those hydrogens think it's a helium, even though it's not really, it is. And here's sort of a Venn diagram, if you will. So here is our +1, here's our proton, and our proton are 2 hydrogens, and here is the 1s orbital and the 1s orbital, and they physically overlap, and the 2 electrons kind of hang out in this space, right? If the 2 electrons are both in this sort of middle ground, both hydrogens see both electrons. And so the way we usually write this is we draw just a little dash in between it. And each dash represents 2 electrons. We can see this again sort of in a bromine. In the case of bromine, each bromine free element has 7 valence electrons and it wants 8. So this is why bromine, and why hydrogen, is a diatomic species. When it's by itself, it's so reactive, 2 bromines pair up, and those will bond, and we get a physical overlap of those orbitals, and so we get a bromine atom, or bromine molecule, because each bromine now has 8 electrons. It has the 7 from it originally had, and then by sharing its 7th one, it gets credit for an additional 1. So now each one of these bromines has 8 electrons around it. They both have a sort of a fake noble gas configuration, even though I don't have a total of 16 electrons. I've only got a total of 14 electrons, but both elements think they have 8 electrons, which makes them happy. So that's, of course, for single bonds. What about for double bonds? So here's carbon dioxide. In carbon dioxide, I have a carbon with 4 valence electrons, and I have 2 oxygens, each with 6 valence electrons. So carbon wants to have an additional 4 electrons around it, and each one of the oxygens wants to have an additional 2 electrons around it. So we'll get the same sort of thing that we have before, physical overlap of 2 sets of orbitals. So in this case, we have 1 electron from this oxygen overlapping with this carbon, 1 electron from this oxygen overlapping with this carbon. But of course, now this carbon sees 1, 2, 3, 4, 5, 6. It still doesn't have an octet. So, and the oxygens only have 7 electrons around them. So we just get more overlap. We end up getting something that looks like this. So each line, again, represents 2 electrons. So this line represents 2 electrons. 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 Every time you join a line, you're basically saying each atom came together, brought 1 electron in an orbital, physically overlapped with 1 electron in another orbital of the other element, and both elements get to see both electrons. So now carbon has 2, 4, 6, 8 electrons. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. This oxygen 1, 2, 3, 4, 5, 6, 7, 8. Everybody's got an octet. Everybody thinks they're happy. What about nitrogen? Nitrogen only has 5 valence electrons. It is also one of those 7 diatomics. And each nitrogen has 5 valence electrons. It wants to have 8 valence electrons. So we overlap 1, 2, 3 times, and we get our nitrogen diatomic. It now has a triple bond. 6 electrons being total electrons being shared, 3 from each. Each nitrogen sees 1, 2, 3, 4, 5, 6, 7, 8. Each nitrogen has an octet, is happy. Now, one of the elements that was not a diatomic that you might think might have a diatomic would be that, in fact, of carbon. Because carbon has 4 valence electrons, so why doesn't carbon make a quadruple bond? And even just the saying the word quadruple bond, any of you who've taken chemistry would kind of go, wait, there's no such thing as a quadruple bond. And that's right. And the reason that it's not is it has to do with the fact that these are physical orbitals where these electrons are, and by manipulating the physical atom where those orbitals are, the most overlap you can have is a triple bond. It's physically impossible to overlap so many orbitals that you actually get 4 sets of electrons being shared. The absolute maximum you can have is only 3 sets of electrons, so a triple bond. So we can't have a quadruple bond, which is why carbon isn't in our list of diatomics.